Hi everyone. In this video, I will be discussing two topics. The first one is the limit of a function at C versus the value of the function at C. And later on, I will be discussing or talking about some limit theorems. Now, for the first topic, mainly, we will simply be comparing the value of the function or what's the limit of the function at C given the limit, and we will be evaluating the function at that certain value of C. So we will be determining if the values of the limit and after evaluating if they will be equal or if they will be not equal. So we will mostly recall our discussions and examples in lesson 1. So the examples that we will be using will be the same with the previous video that I made, my previous discussion. So let us again consider this given function. The limit of the function 1 plus 3x as x approaches 2. Now, if you can still remember, in order for us to get or determine the limit, last time we used the table of values. So we used values from the left and from the right and evaluated those values to our given function. But we made sure that the values that we will be using will not be 2, but values that are near or very close to 2 from the left and from the right. So as you can see here, these are the values from the left of 2, right? So that's 1, 1.4, 1.7, 1.9, 1.95, and so on, up to 1.99999, which is a value very close to 2, but not 2. Now, after substituting this value to our function, we got this answer. So those are, that's determining the limit from the left of the function. Now, from the right side of 2, we have the values 3, 2.5, 2.2, 2.1, 2.03, 2.09, 2.005, and 2.00001, which again is a value from the right of 2, which is very, very close to 2, but not exactly 2. Now, substituting all these values, especially the last one, we got this answer. So that's 7.000003. Now, taking into consideration these answers, we can conclude that the limit of the function 1 plus 3x as x approaches 2 is 7, because these values, this one and this one, these are approaching 7. Now, that's just a review on how you get the limit or determine the limit of the function using values of C both from the left and from the right. Values close to C from the left and from the right. So in comparison, f of 2 is also equal to 7. So how do we get f of 2? Simply substitute the value of C or x to our function. So since our function is 1 plus 3x, I'm sorry. So again, since our function is 1 plus 3x, simply substitute 2 as the value of x. That's 1 plus 3 times 2, and that is 7. Okay? So in this example, the limit of the function as x approaches 2 and f of 2 are equal. So notice that the same holds for the next examples discussed. So in my previous video or discussion, we also had these examples. So the first one, that's the limit of x squared plus 1 as x approaches -1. And the limit of the function is 2. So again, you already know how to do that. Substitute values close to C, both from the left and from the right. Close or approaching C from the left and from the right. Substitute that to our given function. Now, for the value of the function at C itself, which is -1, so simply substitute that is x squared plus 1. So that's -1 squared plus 1. So that's 1 plus 1, that's 2. So in this case, the limit of the function and the value of the function at C are equal. For the second one, the limit of the absolute value of x as x approaches 0 is 0. Again, you can use a table of values for that. Here, simply substitute. So absolute value of 0 is 0. So those are cases wherein the limit of the function and the value of the function at C are equal. This, however, is not always the case. Okay, it's not always the case that the limit of the function at C and the value of the function at C are or will be equal. So let us consider the function, this piecewise function. F of x is equal to absolute value of x if x is not equal to 0, and 2 if x is equal to 0. So in contrast to the second example above, the entries are now unequal. So determining the limit of the function at C, or as x approaches C, I mean. So here we will be using this part of the function, since C should not be equal to 0. It can be close to 0 but not 0. So that's the absolute value of x. So the limit of the function is 0. Now for the value of the function at 0 itself, for at exactly 0, we'll be using this one since x is equal to 0, and that will give us 2. So therefore, for this case, the limit of the function at C and the value of the function at C are now unequal. So question, does this in any way affect the existence of the limit? So the answer is not at all. This example shows that the limit of the function as x approaches C and f of C may be distinct. So there will be times that those values will be equal, and there will be times that those values will be unequal. Furthermore, let's consider the third example in lesson 1 or on the previous module. So given the function f of x is equal to x plus 1 if x is less than 4, and the quantity of x minus 4 squared plus 3 if x is greater than or equal to 4. Now, for the limit of the function as x approaches C, the limit does not exist. So again, you can use a table of values. For the left side, you can use, or we'll be using this one since that's x is less than 4. For the right side, we'll be using this one since that's x is greater than or equal to 4. So it so happened that the limit from the left and the right side are not equal, so meaning the limit does not exist. Now for the value of the function at C, so which is 4, we'll be using the second one. So this one right here, since that's equal, x is greater than or equal to 4, meaning 4 is included in this part of the function. So substituting, that's 4 minus 4 squared plus 3. To substitute 4 right here, that's 0 squared, that's 0. So once again, we see that the limit of the function as x approaches c and f of c are not the same in this case. Okay. Now, a review of the graph in the previous lesson is given below, which will also emphasize in order for us to determine whether the limit of the function as x approaches c and at f of c or at c will be equal or not. So we restate the conclusions, adding the respective values of f of c. So for number 1, the limit of the function as x approaches -2. So we have here -2. So as we can see here in our graph, as x approaches -2 from the left and from the right, the limit is approaching 1. Okay, that's 1. And at f of -2, this point right here, you can see that the value of the function is still 1, meaning they are equal. For number 2, the limit of the function as x approaches 0 is 3. So here, this part right here. So as x approaches 0 from the left and from the right, so the value or the function is approaching 3. Okay. And f of 0 does not exist or is undefined. If you can still remember during your junior high school discussions, whenever you see this one, this open circle right there, that means that that part is excluded. It's not included in the set of the values in the function. So meaning at that point right there, 0, or I mean, yeah, 3 is not included. So meaning at f of 0, the function does not exist or is undefined. Okay. Now for number 3, the limit of f of x as x approaches 3 does not exist. Let's try to look here in our graph. So as x approaches, or as the function approaches 3 from the left, the value there is, the limit is 0. As x approaches 3 from the right, the limit is 4. So meaning the function or the limit does not exist. Now for the value of the function at c itself, which is 3, you can see right here, that is equal to 2. Okay. So here we have some examples. Let me try to discuss these one. So example 1, consider now the function f of x is equal to x cubed minus 1. So compare the limit of the function as x approaches 1 and f of 1. So in this example, f of 1 and the limit of the function as x approaches 1 are equal. So let's try to solve for the limit or determine the limit. So let's start from the left. Let's choose a value that is close to 1 from the left. So let's say we can have 0.99999. And if you evaluate that value to our function, that will give us negative 0.1234. So negative 0.000029. Now from the right side, so from the right of 1, we can choose or we can have 1 point, 0.00001 and evaluating that to our function, that will give us 0.0000. So from these two, we can conclude that the limit of the function as x approaches 1 is 0. Now evaluating the function at c, so that's 0. I'm sorry. Our c is 1. So that's 1 cubed minus 1. That's simply 1 minus 1. I'm sorry. It's 1 minus 1. That is 0. So meaning in this case, the limit of the function as x approaches 1 and f of 1 are equal. Okay? Next, consider the function, the absolute value of x plus 2, and compare the limit of the function as x approaches 0 and f of 0. So we're already given the answer actually, but let's just try to solve. So from the left side of 0, we can choose negative 0.00001. Evaluating that value, substituting to our function, that will give us 1.99999. Okay? So you can actually try to use your calculators in order to verify or in order to check that one. Now from the right of 0, we can choose, or we can have 0.00001, and substituting or evaluating, that's 2.00001. So from these given two, we can conclude that the limit of the function as x approaches 0 is 2. And substituting, that's the absolute value of 0 plus 2. That's the absolute value of 2, which is 2. So for this case, f of 0 and the limit of f of x as x approaches 0 are equal. Okay? Third example. So given the piecewise function, f of x is equal to 2x minus 3. If x is less than or equal to 4, and x squared minus x plus 1 if x is greater than 4. So let's compare the limit of f of x as x approaches 4 and at f of 4. So for the left side, a value that is close to 4, we can have 3.99999. And substituting or evaluating, that will give us 4.99998. So again, you can check or recheck this one in your calculator. By the way, for the left, we will be using this part of the function since that's lesser than or equal to 4. For the right side, a value that is close to 4, we can use 4.00001. We'll be using this part of the function, this one right here, since that is greater than, x is greater than or equal to 4. So substituting, that will give us 13.00007. So as you can see here, the value, the limit from the left and from the right are not equal. Therefore, the limit of the function does not exist. Now, solving for the value of c or f of c. So we will be using the first part of the function since that states that x is less than or equal to 4. So that's 2 times 4 minus 3 That is 8 minus 3, which is 5. Therefore, the limit of the function as x approaches 4 and f of 4 are not equal. Next, let's consider the given graph. So given the following graph of the function, determine if the limit of f of x as x approaches c is equal to f of c at these given values. So number 1, the limit of the function as x approaches -2. So this part right here, we can see that as x approaches 2 from the left and from the right side, the limit is approaching 3. And at f of -2, which is this point right here, the value is also 3, meaning they are equal. For the second example, the limit of the function as x approaches 0, both from the left and from the right. So it is approaching 5. Now at f of 0 itself, which is again this point, so the value is still 5. So the limit of the function as x approaches 0 and f of 0 are equal. Third one, so the limit of the function as x approaches 3. So from the left, it's 2. From the right, it's 3, meaning the limit does not exist. And at 3, so this one, f of 3 is equal to 6. So meaning the limit of the function as x approaches 3 and f of 3 are not equal. Okay. So we have here supplementary problems. I will be asking you to answer these problems. I will be giving the instructions in our group chat. Now let's proceed to the next topic, the illustration of the different limit theorems. By the way, if you have questions, if you have clarifications, feel free to ask so that I will be able to answer your questions or your queries. In the following statements, take note, C is a constant. Constant meaning it's a number. Since numbers are constants, it will never change its value. And F and G are functions which may or may not have C in their domain. So it can be included or excluded in the domain of those given functions. So the first theorem that we have is the limit of a constant is itself. If k is any constant, then the limit of k as x approaches c is still k. So for example, the limit of 2 as x approaches c is still 2. Because again, a constant will never change its value. 1 will always be 1, 2 will always be 2, 3 will always be 3. So the limit of that function will be the constant itself. Second example, the limit of negative 3.14 as x approaches c. Again, it's the constant itself, which is negative 3.14. Letter C, or third example, the limit of 789 as x approaches c is, again, the constant itself, which is 789. I think that's the easiest theorem among all the limit theorems. Next, number 2, the limit of x as x approaches c is equal to c. So this may be thought of as the substitution law because x is simply substituted by c. Now, as we all know, x is a variable and its value varies, it changes, so depending upon the given value. So the limit of x as x approaches c is equal to c. So we will simply substitute the value of c to our variable. Letter A, the limit of x as x approaches 9 is simply 9. Again, just mere substitution. Letter B, the limit of x as x approaches 0.005 is 0.005. Letter C, the limit of x as x approaches -10 is, of course, -10. I think that's clear. That's very easy. So for the remaining theorems, we will assume the limits of f and g both exist as x approaches c and that they are L and M respectively. In other words, the limit of f of x as x approaches c is L and the limit of g of x as x approaches c is M. So theorem number 3, the constant multiple theorem. This says that the limit of a multiple of a function is simply the multiple of the limit of the function. So in this case, there is a constant before the function. So the limit of k times f of x as x approaches c is k times the limit of f of x as x approaches c, which will be equal to k times L. So what happened here is if there is a constant prior to the function, so simply move that constant before or outside of the limit. So k will be placed before the limit of the function. Then solve for the limit of the function, then later on multiply the constant by the limit of the function. So for example, given that the limit of f of x as x approaches c is 4, so we know that the limit is 4. So letter A, the limit of 8 times f of x as x approaches c, again place the constant outside or before the limit of the function here. Then evaluate or determine the limit, which is already given, which is 4. Then multiply 8 times 4, that is 32. Letter B, the limit of -11 times f of x as x approaches c, again, put the constant or place the constant before the limit of the function, then evaluate the limit, which is already given, which that is 4, then simply multiply, that will give us -44. Letter C, the limit of 3/2 times f of x as x approaches c, again place the constant outside or before the limit of the function, evaluate, that's 4. So 3/2 times 4 is 6. So it's 3/2 times 4. I'm sorry. Times 4. That's simply numerator to numerator. That's 12. It's 12 over 2, which is 6. Now, the fourth theorem is the addition theorem. This says that the limit of a sum of functions is the sum of the limits of the individual functions. Subtraction is also included in this law. That is, the limit of a difference of functions, the difference of their limits. So, the limit of f of x plus g of x as x approaches c is simply their individual limits added together. So that's L plus M. Same with the subtraction. So the limit of f of x minus g of x as x approaches c, that's the limit of their individual functions being subtracted. So that's L minus M. So to better understand that one, we have an example. So suppose you're given the limit of f of x as x approaches c is 4. This is given. And the limit of g of x as x approaches c is -5. So solving for the sum of their limits, that's simply 4 plus -5, or simply 4 minus 5, which is -1. For letter B, that's the difference of their individual limits that's already given. That's 4 minus -5. So that will become positive, which will give us 9. Number 5, the multiplication theorem. This is similar to the addition theorem, with multiplication replacing addition as the operation involved. Thus, the limit of a product of functions is equal to the product of their limits. So, the limit of f of x times g of x as x approaches c is equal to the limit of f of x as x approaches c times the limit of g of x as x approaches c, or simply L times m. So, that's simply the product of their individual limits. So, as an example, using the given above, the one earlier, so the limit of f of x times g of x as x approaches c. So simply multiply their individual limits. That's 4 times -5, which is -20. So we have some remarks over here. Take note. The addition and multiplication theorems may be applied to sums, differences, and products of more than two functions. So we can have the sum, the difference, and the product of more than two functions. You can have 3, 4, 5 functions, and so on. Second one, the constant multiple theorem, that was the third theorem earlier, is a special case of multiplication theorem. Indeed, in the multiplication theorem, if the first function f of x is replaced by a constant k, the result is the constant multiple theorem. So after evaluating the limit, simply multiply it with the constant. Number 6, next theorem is the division theorem. So this says that the limit of a quotient of function is equal to the quotient of the limits of the individual functions, provided that the denominator limit is not equal to 0, because that will be undefined. So the limit of f of x divided by g of x as x approaches c is the quotient of their individual limits. So that's L over m, again provided that m is not equal to 0 for it not to be undefined. So for example, still using the given earlier, L is 4, M is 5. So simply divide. So that's, I'm sorry, L is 4, M is -5. So that's 4 divided by -5. That's -4/5. If, for example, the limit of f of x or L is 0, and the limit of g of x as x approaches c is -5. So that's fine, since if the numerator is 0, the answer will be 0. But if the limit of f of x as x approaches c or L is 4 and m is 0, it is not possible to evaluate the limit of their quotient, or we may say that the limit does not exist if in the case that the denominator is 0. Next, we have the power theorem. So this theorem states that the limit of an integer power p of a function is just that power of the limit of the function. So given that the limit of f of x as x approaches c is equal to L, then the limit of f of x raised to p as x approaches c is simply the limit of f of x as x approaches c raised to p is equal to simply the limit raised to the exponent or the power. So for example, letter A, Given that the limit of the function as x approaches c is 4, then the limit of f of x cube as x approaches c. So we already know the limit, which is 4 raised to the power of 3. So that's 4 times 4 times 4, which is 64. Letter B, second example. So still the same limit. Here, the exponent or the power is negative 2. Now, if you can still remember, if the exponent is negative, you will solve or get the reciprocal of your base. So our base here is 4. The reciprocal of 4 is simply 1 over 4. Then, from being a negative exponent, it will now become positive. So it will become positive, then simplify, that's 1 over 16. So here, that's the limit of the function. Number 8, and this is the last theorem. So the radical or the root theorem. This is the inverse of the power rule or the power theorem. This theorem states that if n is a positive integer, the limit of the nth root of a function is just the nth root of the limit of the function, provided the nth root of the limit is a real number. Thus, it is important to keep in mind that if n is even, the limit of the function must be positive. So, given the limit of the function as x approaches c is L, then the limit of the nth root of f of x as x approaches c is the nth root of the limit of the function as x approaches c, or that's simply the nth root of L. So to better understand, let's have an example. So given that f of x, the limit of f of x as x approaches c is 4, then solving for the square root of the function, the limit of the square root of the function. So we know that L is 4, extracting the root, that is 2, because the square root of 4 is 2. Letter B, given the limit of the function as x approaches c is negative 4, then it is not possible to evaluate the limit of the square root of f of x as x approaches c, because as we know, if you find the square root of a negative number, that will result to an imaginary number, or it is not a real number. So I have here solved examples. You can check these examples. And for the supplementary problems, I would be asking you to answer some of these items. I will just be giving the instruction in our group chat. Again, if you have questions, clarifications, feel free to ask. You can ask in the comment section below, or you can ask it in our group chat, so that you will be answered, or your questions will be entertained. So that's it for this discussion. I hope you learned something. Thank you so much for listening. You take care always. Bye-bye for now.